Log on, tune in, find out. Another good idea from Cambridge.
I will explain a method of investigating oscillatory functions. The method is based on a definition which involves both qualitative and quantitative aspects of the oscillation phenomena. One of the quantitative characteristics of oscillations is the oscillatory time, which answers the question, roughly speaking, how long at most a quantity can be of one sign. So the evolution of a quantity is described by a real function, continuous, but the definition applies equally to general measurable functions, where this function is defined on an interval either semi-infinite, t0 plus infinity, or on the whole real axis. We say that the measurable function ut is oscillatory about 0 for t tending to infinity if there exists the so-called oscillatory time, a positive constant, capital theta, such that for any interval j, the length of which is greater than capital theta, the function assumes both positive and negative values. That means the measure of t where ut is positive, and also where the u is negative is positive. This means that u changes the sign on every such interval j, and consequently, for u continuous, there is a root of u in j. Under a very general situation, we have another equivalent definition, which says that if a function is non-zero, then it is oscillatory if and only if the following implication holds. If ut is non-negative or non-positive on an interval j, subinterval of j0, then necessarily the length of j is less or equal to theta. Yes, this is satisfied if, for example, we study solutions of differential equations and initial value problem for this equation is uniquely solvable. Classical examples of oscillatory functions: continuous periodic functions or almost periodic functions with the mean value 0. Oscillatory time that can be chosen the same for all non-constant solutions, or at least for a class of all solutions of the given equation, is called the uniform oscillatory time, and the equation is then called the uniformly oscillatory equation. This definition was used especially not only for solutions of ordinary equations, but also for partial differential equations by Alain Aron, Thierry Cazenave, and Henrik Zuazua. I am glad to mention his name once more in this afternoon. They used the so-called globally oscillatory solution functions. And not only for conservative systems, but also for dissipative systems, as we shall see. A few examples. Harmonic oscillator is governed by the equation double dot u, dot is the derivative with respect to time, plus q u is equal to 0. And if q is greater than 0, we know the formula for all non-zero solution is known. It is a sine square root q t plus phi, where a is greater than 0.
Forgot this.
Ah. A is greater than 0, phi belongs to an interval, the length of which is 2 pi, and we can see that the uniform oscillatory time is capital theta is pi over the square root of q. Linear oscillations with damping or amplification. Again, we can see the equation with p and q constants, and if p square is less than q, then this is the formula for general solutions. And again, we can derive that the uniform oscillatory time for this equation is capital theta is equal to pi over square root of q minus p square. We can here we can see the oscillatory time in this picture, in this figure. Nonlinear oscillations, or more specifically, the equation w double dot u plus f of t double dot dot u plus g t u is equal to 0. The oscillation conditions which are due to zu azua are the following. U g t u is greater than or equal to q u square for all t from our interval j0 and u from r, and the absolute value of f t b is less or equal to a constant denoted by 2m, absolute value of v. And q is greater than 0 and m is less than square root of q. The evaluation of the uniform oscillatory time can be given in terms of quantities q and m by means of the so-called summit function. I would like to show the idea of the proof of this method of investigating oscillatory solutions by means of the linear type equations. So here we can see the equation double dot u plus f of u u dot u plus g t u is equal to 0. And since we study oscillatory properties near plus infinity, so we assume that we have at disposal some solutions, the so-called global solutions, which form the set U, where the solutions of this equation are defined on t0 plus infinity. We establish conditions on function f and g under which there exists a number capital theta such that any function u from u is oscillatory with the same oscillatory time theta. An estimate for the oscillatory time is given again in terms of the summit function. Oscillatory oscillation assumptions. Let us denote the antiderivative of the function f by capital F. And assume that there exists constant q, m, and capital M such that q is greater than 0 and this system of inequalities holds. Moreover, ug is greater or equal to qu squared, and then the following inequalities are valid, where u plus means the positive part of the number, u minus negative part of the number, and analogously for functions. So if we have a function u, we can see u plus, u minus. I suppose more instructive is the graphical expression of these conditions, namely that the graph of capital F should belong to the dotted domain in figure 1, and G belongs to the dotted set in figure 3, uniformly with respect to T. So these two conditions are oscillatory conditions which ensure oscillatory properties of solutions of the linear type equation 1. Under the above assumptions, there exists the so-called uniform oscillatory time, capital theta, such that any non-zero u from the calligraphic u is oscillatory with the same oscillatory time theta. We can say that this equation is uniformly oscillatory, and the uniform oscillatory time is given by the following formula, where we can see the summit function theta, which is a function of two variables. This is a given function, explicitly given function, and the uniform oscillatory time is given just by this formula. This function is defined for q greater than 0 and p greater than minus square root of q. If we compare this value theta with values of oscillatory time in example 1 and 2, we can see that this specific values of theta, for example in example 2, are just pi over q minus square root of q minus p square, and in example 1, where capital M is equal to 0, theta is equal to small theta q 0, and it is just the value pi over the square root of q. Idea of the proof. The proof is based on a special choice of test functions. So let us assume that we have at our disposal the following function gamma, which is C2 on the interval tau 1, tau 2, which is positive and on the interval tau 1, tau 2, and 0 is at the ends of this interval. The derivative at the left end of this interval is positive, and at the right end of this interval negative. It is a Bell function, and we obtain 0 is equal u tau 1 gamma dot gamma tau 1 minus u tau 2 dot gamma tau 2 plus integral tau 1 tau 2 from double dot gamma u minus capital Fu dot gamma plus g gamma u dt. And now these are crucial estimates of this method, namely Fu times dot gamma plus positive part of the derivative is, according to our assumptions, less or equal to 2m u plus dot gamma plus, and 2m u plus dot gamma minus is less or equal f of u dot gamma minus. The second inequality is the same as the third inequality, and the first and the third inequality together determines, give the following inequality: Fu, capital F of u dot gamma is less or equal to capital M dot gamma plus minus M dot gamma minus u plus. And now, if we suppose that u is non-negative in interval tau 1, tau 2, so we obtain 0 is greater or equal to this integral. We use the estimates we have just derived, and this is equal epsilon integral tau 1, tau 2 gamma u dt. The last equality is true under the assumption that the function gamma satisfies, moreover, this differential equation with jumping nonlinearities in the first derivative. Such a function exists, can be constructed, explicit formula is known. So we can do conclusion. Epsilon that integral gamma u dt is less or equal to 0. Epsilon is greater, is supposed to be greater than 0. Gamma is 0. Gamma is greater than 0. Gamma is greater than 0. And if we assume u greater or equal to 0 in this interval, so we have necessarily u is equal identically in tau 1, tau 2, and consequently in the whole interval j0. Analogously, if u is less or equal to 0 in interval tau 1, tau 2, we get this inequality, and again u is equal identically to 0. Such a function gamma can be constructed by means of the so-called universal comparison function on any subinterval of j0 whenever its length is specified is sufficiently large, namely greater than the oscillatory time, by means of the so-called summit function. Explicit forms and more details about these two functions can be seen in this article, and here we can see the form of the universal function, which is the function which defines the function gamma. 0, 0, derivative is here positive, here negative. Here you can see the summit function theta q p, and this is the oscillatory time. Now, oscillatory diffusion equation. Classical diffusion convection equation for the function eta can be seen here. d eta by dt divergence k gradient eta minus divergence beta v plus g. This equation stems from two laws: the fundamental balance law, mass energy conservation law, d eta by dt plus divergence w is equal to g, which is combined with the classical constitutive law of the form w is equal to minus k gradient eta plus beta v. Eta is density of some substance distributed in a medium, mass energy in a medium. W, flux density vector. B, flow field for the medium in which the substance is moving. K is a coefficient in general tensor. G, time rate of change of the density of sources. Very often beta is equal a constant times eta, divergence v is equal to 0. Then the equation becomes d eta by dt minus divergence k gradient eta plus gamma v gradient eta is equal to g. Equations of this type arise, for example, in the theory of the heat conduction, the theory of diffusion, and the theory of fluid flow in porous medium. These two laws I mentioned give rise to parabolic equation 7. This means that there is infinite propagation velocity for the substance, mass energy. So this equation cannot describe high speed processes. In order to remove the paradox of the infinite velocity of propagation of disturbances, Cattaneo in 1958 proposed to modify the classical time-independent constitutive relation. He studied heat conduction, so it was Fourier law, by adding a time derivative flux term. It is interesting that for the need of do some improvements in the diffusion equation, it was already Einstein, who pointed out the need of overcoming this inconvenience. So Cattaneo managed to obtain an equation where the speed of velocity or speed for the substance is already finite by adding a time derivative flux term. This term, tau dv by dt plus v equals minus k gradient eta plus beta v. This constant t is called relaxation time, and the flux, what is the meaning of this left-hand side of the constitutive law? We can see here approximatively that tau dv by t plus w is equal to this fraction, and consequently it is w t plus tau. This means that the flux does not start at time t when the gradient is imposed, but at the time t plus tau. So it is something like measure of inertia effects. The modified constitutive relation in this sense, together with the conservation principle, yield then the hyperbolic type equation, and the propagation velocity is finite. So we can see the equation here. This equation removes already the paradox of the instantaneous propagation of disturbances, but as well as some other phenomena typical for parabolic equations, such as the smoothing effect, irreversibility of time, and may possess solutions oscillating for t going to plus infinity. There is a number of papers dealing with Cattaneo type heap models, non-Fickian diffusion, Darcy law with relaxation, etc. In abstract setting, let omega be a bounded domain with sufficiently regular boundary, tau 0 and alpha 0 positive constants, xu, sigma of xu is a function with suitably smoothness and growth conditions. Capital A, B, let be a matrix of functions which is symmetric and positive definite, and B, capital B, is a vector of functions from C1, and C is a function. Continuous. We define operator L as minus divergence AX gradient U plus BX gradient U plus CXU, which is assumed to operate on a closed subspace V, which is subspace of the Sobolev space and contains Sobolev space V120. And the equation we are interested in is the following hyperbolic equation. 11. Now, assumptions ensuring the oscillatory character of solutions. Again, we assume the existence and uniqueness of at least energy solutions of the corresponding initial boundary value problem, and we assume that there are solutions which are defined on 0 plus infinity. That means that there are global solutions, and the set of all global solutions is denoted by calligraphic U. Let us assume that the adjoint operator has the so-called principal eigenvalue and principal eigenfunction V1, which are both real, and V1 is positive, bounded to positive. Let us remark that I do not assume that L is a symmetric operator. We establish conditions ensuring oscillatory properties.